So now the Phalos instrument will measure the angular dependence of OLED emitter film, where we excite with blue light, and the green is the photoluminescence that is measured versus viewing angle.
So right here with Fluxim. Hello.
Yes, my name is Beat Ruhstaller. I'm the founder of this company. We have targeted the OLED industry and research community worldwide. And this is our newest instrument that helps to improve OLED devices and OLED materials. We have started with simulation software in the past.
So why are we simulating a flexible OLED?
Because this is cutting edge. Displays are going to be flexible, and all these new display pixels, they need to be optimized. The layer sequence of the OLEDs need to be optimized. We can simulate the electrical property of the OLEDs, but also the light emission, how much light is coupled out or is trapped in the substrate. And we can do angular measurements. This data shown here is exactly taken from this instrument next to it. These purple data points are measured, and the green line is the simulation. And thanks to the good agreement, we can get the material parameter, namely the molecular orientation of the emitter film is a key optimization parameters. The more horizontal the molecules, the more light outcoupled to the air.
So what are we looking at right now? What's happening? What's it turning and measuring something?
Yes, that's the blue LED, UV blue kind of that you see is exciting the organic film. The organic film emits green light. That would be the material in an OLED display of the green pixel material. And here it's just to get this data that we just saw in the product flyer. The angular spectra are measured, and the angular spectra are then integrated, and in the end we plot the S and P polarized emission intensity of the OLED film, and by this we can determine the emitter orientation by doing a simulation with the Setfos software that gives these lines that fit the measured data. And so it's innovative that now this instrument can do optical excitation as well as electrical excitation.
So what each part is doing right here?
Right here we have a sample holder stage with a macro lens.
So it's holding a sample of an OLED display?
It's not a complete display. Basically it's an emitter layer, a layer of an OLED. We see here there's a glass. It looks transparent, but you just saw before, if we illuminate with the blue light, then it will luminesce in green. And this transparent layer is part of an OLED pixel in the end.
So this is part of an OLED display or pixel? What do you say?
Yes, this is a large area film. This film that looks transparent will then be used in an OLED. This is now a research OLED pixel. There are a few OLEDs here inside, just 4 of them. It's not a high resolution display, it's just made to improve and optimize an OLED stack. OLED stack means there are thin films of OLED materials that make up the OLEDs. And instead of this film, I could also place the OLED here and directly excite the OLED. Instead of doing an optical excitation, I can also do electrical excitation called electroluminescence.
Which part is the OLED?
It's not so easy to see because there is an encapsulation glass and a metallic cover. Usually if I have an electrical contact, then the light would come out from this side. But I would have to remove this sample and then place the OLED here, and then make sure to contact the electrical pads. But now, I would need still to change the vertical position here in order to touch these pads.
So who would be using this?
We have customers in the OLED industry, the big players from Korea, in Japan, in China, and everywhere in the world.
So how do they put their samples in there or something?
They have to make in their own labs. They are making such research samples in order to play around these new chemicals that the suppliers of the material give them, and they need to select the right materials for the highest performance OLEDs that are stable, that are highly efficient. So we're giving enabling tools to the industry.
So this is the Phelos.
Phelos, yep.
Phelos. And this is for these kind of companies to buy?
Yes.
And they put in their labs?
Exactly, in their research labs to have so they can prepare the next generation of OLED displays.
So, what's your background? Where are you based?
We're based in Winterthur, Switzerland. That's not far from Zurich. We are a spin-off company from Zurich University of Applied Science, and we have been around since 12 years. We are developing and then selling worldwide. We have distribution partners in Asia, and we have smart people that do user-friendly software. Because not only hardware, we started out with simulation software 12 years ago.
So it's with the university?
No, we are already outside. We spent 5 years in the Technopark Winterthur, and since February this year we have an external, larger office outside of the university.
And you hire people from the university then, or?
Yes, we
How
sometimes
many people are you?
we are 12 full-time equivalents that are doing software development, tech support and marketing, as well as equipment development.
And this is made in Switzerland?
This is made in Switzerland.
And how many did you make so far? Is it a secret or?
This one is brand new because it's a second prototype, and we are delivering in 2 weeks. We're delivering to the customer. For this other measurement equipment, we have already sold several dozens of these equipments to the worldwide OLED and solar cell industry. So all the researchers that make next generation solar cells or OLEDs, they can benefit from a very easy to use and very fast and reliable
What's the main
equipment.
difference between that and this?
The main difference, this is focused on electrical properties of OLEDs, where we only look at the, for instance, transient electroluminescence measures only the time-dependent light output, and here we have angular resolution of the light coming out. We get the spectrum of light, angular dependence, so it's complementary. This is more optical analysis, and this is more electrical analysis.
And what's next?
What's next? We already have something in the pipeline, which is an extension. We also want to show that, or to help the people to analyze the degradation phenomena that still occur. So this is a stress test system that can do accelerated lifetime testing at higher current density and higher temperatures. We have 4 different temperatures here in these stages. Multi-channel stressing can be done here, and to monitor the decay of the performance of the OLEDs. And then we want to combine it. The user, the customer, can do this in combination with this other instrument. At every 15 minutes after stressing, we would remeasure the device performance, and we already have some examples here. You see that there's a systematic change from a fresh to a degraded device, and by doing more than this simple decay curve, we can actually try to understand, the customer understands why his OLED device is degrading.
And so that was with the blue or some other things in OLED that are degrading?
Yes,
or?
exactly. Blue is still a challenge for OLED displays. The blue is not as stable as green and red, and there is a lot of chemical synthesis effort going on to improve more the material that emits blue light, and our research tools help in this challenge.
And there's going to be lots of flexible displays, right? That's the future, right?
Yes, we have a lot of customers that are working towards flexible displays.
And so that's going to be even printed OLEDs?
Yes, flexible, done by inkjet printing of liquid OLED materials.
And then checked out and optimized with your tools?
Exactly.
And you're the best at doing this in the world?
I believe we are leading edge in this respect.